You're listening to the We Are Libertarians podcast network. Find all of our shows at wearelibertarians.com.
Episode 107, The Paradox.
Welcome to The Paradox with your attending, Dr. Eric Larson. He is a practicing anesthesiologist and clinical assistant professor at Michigan State University College of Human Medicine. Listen in as he takes you behind the scenes of what practicing medicine in today's ever-changing world is like with another doctor. The Paradox is a fun and accidentally informative show for physicians, patients, or anyone who has ever found themselves in a waiting room.
Welcome to The Paradox. I'm your host, Dr. Eric Larson. Thank you for joining me as we explore the U.S. medical system in a fun and informative format through expert analysis. And today's expert, Dr. Jason Fung, joins me again, this time to talk about cancer. Many are probably familiar with Dr. Jason Fung for his work on intermittent fasting and the treatment of diabetes and obesity with fasting. So it might seem a little bit strange that a nephrologist who specializes in fasting and diabetes is writing a book about cancer. But actually it makes a lot more sense you might imagine. It turns out that one of the leading factors leading to cancer is obesity. And because of the obesity epidemic in the United States and the rest of the Western world, it now makes cancer one of the top killers of people. And because of our relatively ineffectiveness in treating cancer, and also our effectiveness in treating heart disease, cancer has almost eclipsed heart disease as the number one killer of Americans. And so the obvious question is, why exactly does obesity affect your rate of cancer? Well, that gets into a better discussion about exactly why we get cancer. In fact, things that I had never really considered, and I've been in medical school, and the thinking since the 90s has changed significantly from today, is that cancer is just abnormal growth and is caused by genetic mutations. But if you think about it, that's really a simple way of looking at cancer, because if you're in the operating room, or if you're a surgeon, or even if you're a pathologist, what's striking about cancer is, A, it's extremely common. Lots of people get cancer. But also, all the cancers end up looking exactly the same. How is this possible? Because if you think about it, cancer originates from so many different types of cells. Bone, breast, pancreas, colon, brain. You'd think, therefore, that cancers will look different. And although they behave differently and the treatment's somewhat different as far as the chemotherapeutic agents, essentially all the cancers, if given enough time to metastasize and differentiate, you'll find that they all look exactly the same. That's really strange, and that suggests a more common ancestor for all cancers. And that's what we really discussed in today's episode. And that's what I did not know after medical school. It seemed like it was just random mutations. The book we're going to discuss is called The Cancer Code. And for anyone who's even a little bit interested in cancer, maybe you've had a family member die of cancer, or you've had cancer yourself, maybe you treat cancer. It is certainly a fascinating book for people who are both medically and non-medically inclined. You're going to learn a lot about cancer, why it exists, the origins of cancer as best we can determine at this point, and how our previous understanding and treatment modalities have changed based on what we think is a cause of cancer. And you'll see how the new thinking, what he calls Paradigm 3.0, is significantly different than what previous thinking, which is what I learned when I was in medical school in the 90s and 2000s, of just genetic mutations. As with most scientific discoveries, it builds upon the previous knowledge. And so what we knew in the past is in fact true, but it was more rudimentary than what we understand now. Anyway, we'll get into all that in the show. I think you're going to find it fascinating, and I hope you share this with your friends. Make sure you subscribe to the show if you've not already subscribed on whatever podcast player you use. We're also approaching the end of the year, which means the next year, which obviously everyone's happy to see 2020 leave and them far behind in the rearview mirror. But also, it's going to be the launch of the Doctor Podcast Network. As you may know, the Doctor Podcast Network launches on January 1st, includes a Paradox and a bunch of other really great shows by other physicians, and one where you think you can find all sorts of things about finances, self-help, medicine, and I guess mine's just a general show about medicine, medical delivery system, and quite frankly, anything that I think that's interesting. You can find out more about that at drpodcastnetwork.com. Obviously, you can find the show notes for this page at theparadox.com/107. I'd also really highly recommend this book, The Cancer Code by Dr. Fung. It's not too late to jump in and order on to Amazon and get it for the stocking stuffer for your friends. Again, it's a great read. It's quick, very understandable, digestible, and I don't know, I just can't recommend enough. I found it a really fantastic book, and one that, even if you're not a big fan of nonfiction, it's certainly one I think you'll get a lot out of. But without further ado, Dr. Jason Fung and Understanding Cancer. Enjoy. All right, welcome. I'm here with my friend, Dr. Jason Fung, who's a nephrologist in Toronto, Canada. He's the author of a lot of books, Diabetes Code, Obesity Code, The Complete Guide to Fasting, Life in the Fasting Lane, and some cookbooks that'll go along with those books oftentimes. He's an expert on intermittent fasting. And we're going to discuss today his new book that just came out on November 10th called The Cancer Code, which I just finished completely reading about a week or two ago. Fantastic book. It's really interesting. I'm really looking forward to getting into it. So Dr. Fung, thanks so much for being on the show.
Thank you so much. Thanks for having me.
My pleasure. So I guess I'll start with the most obvious question. You're a nephrologist. You've specialized in intermittent fasting, we'll say, and you wrote a book about cancer. So explain how you made that journey and that leap into talking about something, because you're not an oncologist.
Yeah, it's an interesting thing. So I started looking at the literature from, because of obesity, type 2 diabetes, turns out they're huge risk factors for cancer. And this is not something that was appreciated when I went to medical school in the 90s, for example. So in fact, we never talked about these as a risk for cancer. And then in 2003, of course, there was a very large study that came out from the cancer prevention study, which showed that, in fact, obesity was this big risk factor for certain types of cancer. So breast cancer, colorectal cancer, for example. And the WHO now classifies 13 different cancers as obesity related. So this is something that is sort of well established at this point, but not something that is, it's a relatively sort of recent realization, like less than 20 years ago. We didn't talk about it at all. So that's where I got interested in the question of cancer from that sort of obesity, type 2 diabetes standpoint. But then as I sort of went deeper in, it turned out to be a far more interesting topic than I thought it was. And there's been this huge sort of revolution in the way that we think about cancer and how it develops that had been sort of going on that I hadn't even realized. So that's where I started to, talk about it, not as a sort of oncologist, but, as somebody who's familiar with reading scientific literature. This is sort of the way that things are moving. And it makes a lot of sense. The hypothesis sort of this of cancer as an evolutionary disease is a far more inclusive, interesting, and probably much more correct theory than what I was brought up on, which was sort of the somatic mutation theory, which is this random collection of genetic mutations sort of idea of how cancer develops, right, which doesn't make any sense, actually. And in fact, it's been well disproven. It's not random. Like cancer is not a random thing, because there's things that increase your risk of cancer and things that decrease your risk of cancer. So there's nothing random about it. But yet we thought it was just this sort of random bad luck sort of idea. And that idea still pervades a lot of the way people think about cancer. And that's why I wrote the book. Just to talk about this sort of new recognition and realization, because the oncologists, sometimes I listen to some on the podcast and stuff, they all talk about this, cancer is an evolutionary disease. And it's like a throwaway. And it's like, what do you mean by that? Right? It's like, because I've heard it several times by some of the oncologists. And it's like, how come nobody has explained it to us as physicians? What the heck you actually mean when you say that cancer is an evolutionary disease? And that's what sort of the first part of the book is about. Right. And then the second part is about nutrition, because again, there's been this huge revolution in the way that we look at it, in terms of the obesity question, but also in terms of nutrient sensors versus growth factors, for example. And that's something that we can actually control.
Yeah. Well, I liked the book because it had plenty of science. I mean, there's all kinds of, certainly there's probably 20 pages of endnotes at the end of the book where with all the references to the papers and the footnotes throughout. But it not only had the science, but it sort of explained things in a universally kind of compelling way. It sort of explained sort of the process from when we first thought what cancer was, when we first sort of discovered, I guess you could say, back in ancient times to today. And certainly for me, like you, I went to medical school in the 90s. And so a lot of this stuff, I had no idea any of this had sort of happened as far as, the research and the findings. And so for me, I learned a lot. And I think someone who really knew almost nothing about medicine would still be able to follow the discussion. I mean, there's things that you may not understand, some terminology perhaps, but for the most part, it's written for, I think, a general audience. And so, I would recommend it for both people in medicine and out of medicine, really just to kind of catch up on what's been going on. And to that point, I guess, why don't we just start with sort of cancer, right? I mean, you sort of divide your book generally into 3 points, right? There's the various paradigms of cancer. Why don't you kind of go through, I guess, the paradigms and, what you learned in your research for the book?
Yeah, so, I sort of look at the modern paradigms of cancer sort of in 3 stages, and each stage sort of builds upon the other.
Yeah.
So, in the beginning, we looked at cancer really as a disease of a cell that just grows too much. And the reason these paradigms are important is because that's how you develop treatment. So when you think that, oh, this is a cell that grows too much, then your treatments following that logic are, let's find ways to kill. So that's how you got surgery, which is, cutting it out. And that's how you got radiation, which is just burning it. And that's how you get chemotherapy, which is like poison. It's a selective poison. It's not to say that these are bad. They're actually still form the backbone of modern oncology. So it's not that it was wrong necessarily. It's just that this is the paradigm that they're treating. And unfortunately, it had a lot of side effects, of course, because you're dealing with poisons like chemotherapy. So you're going to have a lot of side effects. And that's where all the chemotherapies get a bad name because your hair falls out and you get nauseated and stuff. And it was a fine paradigm, but again, but it doesn't sort of explain the why. So why are these cells growing too much? And that's where we started to sort of move past this paradigm in the 60s, 70s, and 80s. We started to learn about, genes and stuff. So we said, okay, well, this is now our new paradigm. We moved past and said, why are these cells growing? And we said, well, they're growth genes. And if these growth genes are mutated, then you're going to get too much growth. So it doesn't invalidate sort of paradigm number 1. It sort of moves into sort of paradigm 2, which is now we have genes which cause cells to grow too much. So now you're sort of going one level deeper in understanding. And again, these new paradigm led to new treatments. So now we were no longer trying to find ways to kill. We were trying to find ways to repair the genetic problem. And the first few treatments were just incredible, right? We had imatinib, which was for a type of leukemia, CML. Just an incredible drug. I mean, it was just fantastic, just revolutionized the whole field. And we had trastuzumab, which was for breast cancer. And again, just a revolutionary drug. And they're not trying to kill cells, right? So, it's against the HER2. Trastuzumab, for example, is against the HER2/neu gene. And so you could test for that gene, and then you could only give that drug to those patients that had that mutation. Like, so fantastic. Like, the paradigm was just incredible. So by the 2000s, we were like, oh, we're going to cure cancer, right? We're going to find the 1 or 2 genes that are responsible for breast cancer, 1 or 2 genes that are responsible for colon cancer, and we're just going to cure cancer. That's going to be it, right? That was the 2000s. And that was sort of where I actually had thought about going into oncology for a long time before changing to nephrology. But it was a time of incredible optimism because these drugs had way fewer side effects because you're not trying to kill cells. You're just trying to target this gene. So then you had the Human Genome Project, which sequenced the genes of one entire human being. And we thought, well, this is going to provide the roadmap for cancer. But then the problem is, of course, that person might not have cancer. So that was followed on by the Cancer Genome Atlas, which is an even more ambitious project. So instead of one human being, they're actually going to sequence 33,000 tumors. And then they said, well, let's take those 1,000 colon cancers, compare them, find the 2 genes that are responsible, develop a couple of drugs, and hey, we're done.
Right.
It didn't turn out that way.
Yeah, right.
So what happened was that there wasn't 1 or 2 gene mutations. There was like 50 or 100. And it was just ridiculous because you could have 2 patients, say in your oncology clinic, patient A with colon cancer, patient B with colon cancer, that looked exactly the same stage, pathologically identical, everything. It looks clinically identical. And patient A would have 100 different gene mutations, and patient B would have 100 completely different gene mutations, right? So now this paradigm just falls down because you can't develop 100 drugs for patient A and 100 drugs for patient B. It just doesn't work. And so this is where the promise of this personalized precision medicine really fell down, because after those first initial huge successes, we just basically didn't have anymore, because the paradigm couldn't develop anything else. There's too many mutations. So in 2018, if you look at the catalog, there's a catalog of all the mutations in cancer. The last number was in this 2 years ago, so there's probably more, but it was around 6 million different mutations in the various types of cancer. So it's like, okay, well, you're not going to cure cancer that way. You barely have 10 drugs, right? You're not going to get 6 million drugs. You're several orders of magnitude off. And that was where we were by 2010, sort of in this big pit of despair, because this paradigm, which had seemed so promising, just completely fell down and failed to deliver any other treatments. And if you look at the progression, so cancer and heart disease have always been the two biggest killers of Americans by a long shot, actually. Right. So it's always 1 and 2. In the 60s and 70s, you're sort of twice as likely to die of heart disease than cancer. In 2010 is about the same. So where progress in heart disease had sort of steadily progressed, right? You had better drugs, you had better treatments, you had surgery, you had less invasive surgery, you had all kinds of advances, right? You had devices. So they're making steady progress. And cancer, there's just barely any progress at all. It was really tough. And that's how cancer sort of crept up. And that's where, most people think we're still at, right? But it turns out that's not the case. There's actually been this sort of whole underlying sort of revolution that's gone on that's been unnoticed by doctors like you and me. Now again, you're moving into the third paradigm, which is, again, does not invalidate any of the previous paradigms, but simply goes one level deeper. So you say, okay, now we have gene mutations. We know we have gene mutations in cancer. There's no question about it. But the question is, why are these mutations developing?
Right.
And that's where you say, well, there's a guiding force, because these are not random mutations. If you think about it, it makes sense, because if you have, say, a Black man in 2020 with a colon cancer, and you have a Japanese woman in 1920 with colon cancer, those two colon cancers could look exactly the same, right?
Yeah.
But they're 100 years apart, a world apart, different races, different sexes, and yet somehow each individual colon cancer has developed from a normal colon cell into the exact same identical looking, right down to the pathology, right?
Yeah.
So how does that happen? Because if you have evolution, if you have gene mutations going forward, they're almost never going to look the same. Right. And I say it's like dogs, right? You have wolves which turn into dogs. Now there are dogs that are big and dogs that are small, and dogs that are fast and dogs that are slow, right? There's so many different ways a dog can be from an original sort of wolf ancestor. So this is a very strange problem, because you have two colon cells which have mutated in exactly, like precisely the same way. And how does that actually happen? And the answer to that, again, is what's sort of guiding us now. It clearly is an evolutionary process, but it's not sort of this forward evolution. It's sort of this backwards evolution into a more primitive state. That is what's called an atavism, which is not an evolution sort of forward. It's sort of removing evolutionary, our genes didn't come all at the same time. It's not a big bang of genes sort of thing. Our genes have evolved over time from our evolution, over billions of years. And over time, we sort of add more and add more and add more. And what cancer is the removal of these more recent genes to get to a more primitive state. And what's interesting, I think, about it is that is exactly the term that pathologists have always used.
Yeah.
Right?
Yeah.
These are primitive cells. They are dedifferentiated cells. It's like, anaplasia, the term itself actually means going backwards, right? It's like, this is exactly what we're talking about. It's not a colon cell that's evolving into something new. It's a colon cell that's moving backwards into something older, which is moving towards our evolution from unicellular organisms, which is a fascinating thing that actually explains so many different properties of cancer. That is, why does cancer affect every single cell in the body, right?
Yeah.
Your eyes can have cancer, your heart can have cancer, your placenta can have cancer. Why does every single cell in your body have the potential to become cancerous? That is, that cancer seed is in everything we are, and not just in humans. Every animal practically,
Right.
except perhaps the naked mole rat, right? Every animal can get cancer. And they've even identified it in Hydra, which are this incredibly primitive sort of microscopic organism. So why does every multi-celled animal in existence have the potential to get cancer, right? And why is cancer so common? It's not that cancer is rare. If you believe that you can randomly assemble 50 or 100 different mutations and still survive, well, that would mean that cancer is an incredibly rare disease, but it's not.
Right.
If you look at prostate cancer, you get to 90 and like 1 in 2 men have prostate cancer, right? Breast cancer, 1 in 10 women or 1 in 9 women, whatever you have. It's a hugely, it is very, very common disease. But if you had to assemble 100 different mutations, the chances of that are just it should be like 1 in 10 million women get cancer sort of thing to get 100 mutations that turns out to be cancers. Because the thing is that if you have a mutation, if you have a random mutation, chances are those cells will just die, because random mutations don't, like your cell, their genes are like a finely tuned watch. There's very small chance that you can smash that watch and make it work better.
Yeah,
right?
Yeah.
That's what your genes are. You have a mistake, it doesn't work better. It usually makes it work much worse, right?
Yeah.
So what is going on here? Because when you have a mutation, those cells should just die. Just like when you smash your watch with a hammer, it's garbage, right? You don't smash it and it works even better, right? And smash it 100 times and it works even, oh, that's amazing, right? It just doesn't happen. So this is why the sort of idea of random genetic mutations, which is the somatic mutation theory, just did not explain any of what we saw clinically in medicine. Yet this sort of atavistic evolutionary theory sort of explains all those questions about why cancer develops and so on. And the important part of it is that it leads to new treatments. So the treatments of paradigm 3 are now completely different, because you're not looking for ways to kill. That's paradigm 1. You're not looking ways to change the gene products. That's paradigm 2. The third paradigm is this cancer actually behaves like an invasive species, right? Because it's turning into an invasive species. And you say, oh, that's ridiculous, right? It came from your own body. It's like, yes, but you know that your immune system identifies these cancers as foreign, right?
Yeah.
You know that. There's natural killer cells which will look at this cancerous breast cell or whatever and say, this is a foreign organism, right? So I'm not the one saying it's a foreign organism. It's your body's immune system that says this is a foreign organism. So because we've grown up with cancer, our body has actually produced a lot of anti-cancer defenses, the immune system being one of them. And now, so if you say, well, this is like an invasive species, that's why these things metastasize, because they're trying to move around, right? Just like an infection.
Right.
That's why these things metastasize. This is why, these things grow so much, because they're like invasive organisms. This is why they don't care about the rest of the body, like this breast cell, which will grow until it, pushes your liver out of the way, sort of thing, right? Why doesn't it care about the rest of the body? Because it's like an invasive organism. It just doesn't care. So if that's the case, then you say, well, your immune system is what's tasked with dealing with invasive organisms. Let's boost the immune system. And that's what gives us immunotherapy, which is the next big wave of sort of treatment again, but it's looking at it from a completely different paradigm. You're not killing, you're not changing genes, you're looking at the immune system. And that's where you get the new drugs, for example, all the, PD-1 and, checkpoint inhibitors, you got CAR T therapy, and I go into a couple of other things like adaptive therapy and the abscopal effect, which are super interesting. And again, this is not the end of what we are. I'm sure there will be a fourth paradigm, for example, that will be even more successful. But this is where we are now, and it's a great story of how you can understand how cancer medicine has evolved, the knowledge of cancer has evolved. So it's such a, to me, it's such a fascinating sort of area. And I'm always like, how come nobody's talking about it?
Yeah.
Why didn't somebody tell me? I would have been so interested.
Yeah, no, I found intellectually, it was super interesting because it, like you said, it's totally different than what we learned in medical school. And then it is like most science where it builds on itself. Like the previous foundations were mostly correct, and things we observed and things we could, reproduce and find treatments like, surgery would cure cancer, or at least would slow the progression a lot. But until you know the fundamental reasons why something's occurring, you can't entirely treat it. And so they found treatments for, like you said, for genetic explanations, which actually worked on a few cancers really well, gave us this sort of false hope, maybe you call it. And then found that it failed. It failed when it got to these large genome projects where there was all these, mutations that aren't explained. And even, and as you point in the book, some, there are people who have two breast cancers, let's say, and we know that it's almost certainly they came from the same tumor, but they have different genetic profiles, which it doesn't make any sense, right? You'd expect it to be exactly the same. And I think the biggest thing was really just recognizing that your cells have gone from a cooperative multicellular focus to one that's unicellular, to one that is no longer playing for the team. They're just playing for themselves and for their own survival, like a bacterial infection. And so then you can definitely see why your next approach would look like, well, we have to in some way, have the body itself take care of this problem and find ways to encourage that.
Yeah, and what's interesting is that this idea of intratumoral heterogeneity, because again, this is completely different than what you and I learned, right?
Yeah.
So what you and I learned was that, this cancerous cell suddenly develops all these random mutations, which just happens to really work very well together. And then it basically multiplies. So then the entire mass of your breast cancer, for example, should be genetically sort of homogeneous. Every single cell there should have the same gene, but that's not what you see. In fact, if you take different parts of that same tumor mass, you see completely different mutations. Yeah. So not just different mutations from patient A to patient B, but there's different gene profiles, breast cancer and the lymph node metastasis, and the breast cancer, even within that tumor mass, is heterogeneous. And you can actually trace, and they've done this, I showed that in this paper from the New England Journal of Medicine, you can actually trace how it evolves, right? There's this mutation is added, this mutation is added. And it's like, boy, they've been doing this for like more than almost 10 years. They've been talking about how these things evolve, and I never knew about it, right? Yeah. It's like, wow, that's so interesting. And it leads to this sort of understanding, leads to a lot of new possibilities and new explanations. So screening is one of the things that we sort of thought, okay, well, let's just try and find these cancers at the earliest possible stage.
Right.
But if you get to the very earliest stage, every single cell in our body is potentially cancerous. Right. You may wind up finding a whole lot of stuff that didn't need to be treated, and you may do more harm than good. And in fact, that's what we've been doing, is we've been walking back the recommendations for, say, mammograms. So age 50 and up, is the standard recommendation. People started to do it 40 and up, like I think probably about 15 years ago or something. It became standard to drop that age of screening with the idea that, hey, let's catch this super, super early, right? And this is the important part, is that when you look at it from a different paradigm, you can understand why that might not work. Because then you're just going to catch it at such an early stage that these were cancers that didn't need to be treated. They would never have progressed because they're just, they're being kept in check by the immune system, and you can watch and wait. So prostate cancer is a perfect example where you can take this PSA screening, for example, and instead of saying, oh, there's something here, let's whack it out, you can say, let's do watchful waiting. because that's a perfectly good strategy until it becomes a problem. Because the minute you go in and start trying to treat it, that is surgery and radiation and stuff, you're getting side effects on the other side, right? And what I thought was interesting about breast cancer screening, which is very controversial, of course, is that the reason it fails in a lot of the super early, like, you pick up a lot of this ductal carcinoma in situ, which is a super early stage. It's sort of a precancerous stage, and a lot of people will treat it. And the problem with that screening is that what you have to do in screening is to reduce the amount of late disease that you find. So all your stage 3, stage 4 cancers, you need to reduce that amount. It's not so much reducing, catching early disease. The only benefit is if you can catch early disease and prevent late disease.
Right.
But what the research has shown, and again, this is like not my opinion, this is from the New England Journal of Medicine, is that when you do aggressive screening like that in breast cancer, you don't reduce the amount of late disease that you find, but you about double the amount of early disease that you find, right? But now if you double the early disease, that actually didn't need to be treated, because you're not reducing the late disease. And that's an interesting sort of way to look at it. Just like in South Korea, they did this screening for thyroid cancer. Turns out they just found a whole lot of thyroid cancer, took out a bunch of thyroids, and didn't impact the thyroid, like the mortality, one bit, because you're screening too much. It's overdiagnosis, overtreatment, which you can understand if you understand that, hey, cancer is just a part of the way that multicellular life is done. So you can't just look for it, because if you look for it, you will find it everywhere, right? It's like you're looking for one specific needle in a needle stack, right? It's like, oh, okay, that's going to be an impossible task, right? Because they're not different. These are not different cells. They come from our own cells. So that the sort of understanding lets you sort of see how these things make sense. Like the same with PSA, right? So everybody's sort of walking back, saying maybe we shouldn't do so much PSA. It's very controversial, of course, but mammograms is the same thing. So, but it explains this paradigm is so powerful because it explains all the things that apply to clinical medicine and treatments and everything. It's super interesting.
Yeah, I mean, it really makes you rethink all sorts of things when it comes to treatment. I mean, it makes you really wonder, on some level, do we all have cancer? Like at any one time, like we all have it, probably somewhere there. I mean, we have how many trillions of cells in our body? I mean, the likelihood of us having a couple of cancerous cells is probably pretty high if you were able to look at somehow screen every cell. And the question is, can your body, from your immune system, take out those cells before it becomes a problem?
So mostly it does. And then if you get immune suppressed for whatever reason, that's why you see this big spike in cancer. It's this idea that it's this balance between pro-cancer and anti-cancer forces, because this is sort of something we live with and we've evolved with. It's not something that's completely foreign to us. Like, we've known about cancer for a long time. Our body knows about cancer. That's why it will identify it early and kill it. And, one of the things I thought was very, very interesting is this whole idea of metastasis.
Yes. That
is, we have this idea that metastasis is a late event. That is, your cancer grows and grows and grows, and then at some point it breaks off. Mm-hmm. And it doesn't do that at all. In fact, even before you can detect the cancer, these cells are sloughing off and they're actually in the blood. But their anti-cancer forces are so potent that they will wipe them out like immediately. So now, in fact, it means is that, one, because metastasis is early, you can't just cut stuff out, or you can't just do partial tumor responses because it's already spread out. But the other thing that it means is that we now have the ability to detect these circulating tumor cells. So there's this whole push to do, say, liquid biopsies, where you just take blood, for example. So the cancer cells that slough off, these metastatic cells, they last like in the blood for like an hour or something like that. They get killed like right away. Right. They just don't survive. You can pick them up because our technology has evolved so that you can do these liquid biopsies, and that's, revolutionizing sort of detection and stuff. And again, that's something for the future. It's not here now, but there's a ton of people interested in that. And, this idea that you've got early metastasis explains how metastasis actually happens, because it's an evolutionary process. That is, cancers don't randomly generate the ability, like a breast cancer does not randomly generate the ability to live in the liver, right? The liver is a completely different habitat, right? Why would a breast cancer cell be able to live in the liver? It can't. The old way of thinking, what you and I were taught, was that, hey, it randomly develops this ability, then it lands in the liver, and hey, presto, hey, it's good. It's like, why would it develop that ability? But it doesn't. It evolves that ability, right? Same with the lung, breast cancer, which metastasizes to the lung or to the bone. It evolves that ability because it takes hundreds of different mutations to go from a breast cancer cell that lives in the breast to a breast cancer cell that lives in the bone. It's completely different, right? There's calcium everywhere, and there's all different things all over the place, right? So you can't get those 100 different mutations just by random, right? It doesn't make any sense. It's like a penguin that goes to the Sahara Desert. It doesn't just develop the ability to live in like 40 degrees, 40 Celsius in the heat. It has to evolve that ability, right? And so birds can evolve to be penguins, and birds can evolve to be, ostriches, right? But you have to evolve that ability. So the cancer cell, so what you need, of course, is two things for evolution, which is heterogeneity, genetic heterogeneity, and a selection pressure,
right?
Which is now what you've got, because if you have a metastatic breast cancer, which is starting to metastasize super early, what you get is those breast cancer cells sloughing off into the blood and getting wiped out. But this is a selection pressure. You've got genetic heterogeneity from the breast cancer because it's evolving, and you've got a selection pressure. So at some point, some random mutation will happen that the breast cancer cell will evolve the ability to survive a little bit longer in the blood. And what it does is it doesn't go to the bone immediately. It actually self-seeds. So that breast cancer sloughs off, goes in the blood, is able to survive the blood by some random mutation, and then gets back to the breast cancer cell originally. Now it can survive there, but what it does is it's got a little bit better ability to survive in the blood. It multiplies because it's more aggressive, it takes over, and that's how you get different pockets of cells in the different breast cancer tumor mass. That's why you take two different pieces of tumor, you'll have different genetics because they've evolved differently. And then each time it goes out, it survives a bit better in the blood, a bit better in the blood. And the same thing when it's trying to go to the liver. Waves and waves and waves of breast cancer cells will land on the liver and die before one actually starts to survive. And then that starts the evolutionary process,
right?
Because you've got heterogeneity and you've got a selection pressure. And it's the same way that, birds have evolved all over the world. It's the same way we evolved. It's not different. And that's just what's so interesting about it, because when you think about it from an intellectual standpoint, and not all of this translates into, treatments, but when you think about it, this makes a lot more sense than a random genetic mutation with no genetic heterogeneity, right? So it's a mind-blowing sort of idea and evolution. It's like, wow.
Yeah. Well, and I think that's the thing that, I never really thought about. I mean, anesthesiologist, right? So I don't think a lot about cancer aside from, watching them do the surgery, removing them. But no matter what the cancer is, at some point, they all look exactly the same. I mean, it's real interesting. Like the primary can be pancreas or prostate or breast or colon. Yet when it gets metastasized to the brain, it's just, it's cancer. We don't, or when they find it, we don't know what it is, except we know it's a, cancerous mass, and it's just, we don't even know where it is or where it originated from. Sometimes we'll have those surgeries where someone has, unknown primary, where maybe the primary is what we're taking out. Maybe it's not. We don't know. And so it is very interesting. And as you said, and it's extremely common, right? So to your point earlier that, well, if it's just a couple of genetic mutations, then you would see this, then you could expect to be common. But if it requires hundreds of thousands and they all end up looking exactly the same, it can't be some sort of like random event. I mean, it has to be sort of somehow coded in the DNA, or at least in the normal natural process, right?
Yeah, and that's the idea, is that cancer is actually not. It's sort of the programming that we all evolved with. It's sort of this sort of base sort of subroutine that's there. What happened when we moved from a unicellular organism to multicellular organism is that we added sort of extra sort of playbooks and said, okay, do this, do this, do this. But there was a fundamental shift when we went from unicellular to multicellular, that we went from sort of, competition, that is, unicellular organisms always compete against each other, to cooperation, right? So you've got cells that cooperate together, right? Just like going from an individual to a team sport. You start, in tennis, you compete against everybody else. In soccer or hockey or baseball, you help each other as teammates, right? You compete against other teams, but you don't compete individually, right? Your catcher doesn't try to throw better than your pitcher or whatever, right? It's a team sport. Same thing when you have multicellular organisms. It's a team sport. Your liver and your lung have to, work together. So everybody has to be in the same spot, right? You have to be where you're supposed to be, just like, your goalie has to be in goal. You don't want it running all over the place. And that's why we have things that keep the cells in where it's supposed to be. But as you move towards this sort of unicellular destination, there's no incentive to be in the same place. And that explains why these cells grow all the time, for example. Why do they keep growing, right? Because that's what unicellular organisms do. That's what cancers do. Why are they immortal? That's because that's what unicellular organisms do. Why are they moving all over the place? Right? Why is your breast cancer going to your bone, right? Your breast cell doesn't go to your bone. Why does your breast cancer cell go to your bone? Because that's what unicellular organisms do. Why does it use glycolysis as opposed to oxidative phosphorylation? Because that's what unicellular organisms do. So this is a playbook that is for competition between cells, and that's what we originally started with, and that's why it's present in all our cells. That's why as you evolve towards that same destination, all these cancers, even from a macroscopic, you cut it open, they start looking more and more the same. You can't even tell where they're from. You just say adenocarcinoma, right? It's like, I don't know where it came from. It could have come from lung. It could have come from, liver. It could have come from anywhere that adenocarcinomas come from, because they're all going towards the same destination, which is that sort of unicellular original cancer subroutine. You're just taking off the sort of extraneous stuff and leaving that core, which all looks the same, right? And that's like, this is so interesting because it explains so much of what the sort of somatic mutation theory doesn't explain. Like, there are so many problems with that theory, and yet nobody talks about it. If you go to the American Cancer Society website today, you could say, oh, it's a disease of genetic mutations. It's like, no, it's an evolutionary disease. That's what's guiding your genetic mutations, right? We've moved on from that and gotten to a much more inclusive theory. And the reason we need to know this is because that is going to lead how research is done. That's going to lead to new treatments and all that kind of thing.
Well, and it's funny, as I'm working my way through the book, I kept saying, okay, this is a person who's an expert in intermittent fasting. Here he comes. Here's the next chapter. I'll turn up and he's going to start talking about intermittent fasting. I think maybe you mentioned it once, maybe. And I think you mentioned dietary, just general dietary things a couple times. I mean, clearly there was as you mentioned, there's a recognition that obesity and probably nutrition on some level too, which we don't understand entirely at this point, affects growth, affects cancer. Why don't you talk about that a little bit? Because it wasn't the emphasis of your book. I mean, your book was much more describing sort of what cancer is, where it is, what we're doing about treating it. But obviously you got some thoughts in your back of your mind here of sort of what it means from, like, if I'm just a person out, I'm listening to this podcast right now, I don't have cancer as far as I know. And so I'm not worried about the treatment for, small cell carcinoma of my lung. But what can your thoughts about what people can do now, or sort of what your thoughts are, I guess, for that sort of thing going forward?
Yeah, and it sort of falls along the same lines, because if you're talking of an evolutionary disease, there's two things that are very important in evolution. That is, it's not just the sort of seed, but it's the soil that allows it to bloom. So that is cancer. The seed of cancer is in all of us, right? That's what we've discovered. Every single cell in everybody's body has that seed of cancer. but what is the soil that allows it to bloom or not to bloom? And this is important because you can't do anything about your genetic makeup, like you can't change it, but you can change a lot about the what happens in your body that is going to let it flourish. Because there's this idea that cancer is sort of always with us, but it's not true. Like, you take a Japanese woman in Japan and you move that woman to San Francisco, and the risk to her daughters within a couple of generations is like triple, right? So it's not the genetics, it's the environment, it's what she's eating predominantly, right? And this is what we've discovered. So people who live in Africa who follow a traditional diet, they never got colon cancer. And this is what Dennis Burkitt found when he went to Africa in the 60s and 70s. And so but yet those same Africans, as soon as you change the diet and lifestyle to become more Western, they get colon cancer. So he called it one of the diseases of civilization. And the reason it's important is because what happens is that you can do something about that soil, you can do something about the environment, but you have to know what it is about your environment. And this is what we've spent a lot of time trying to discover. Like, is it fiber that's important? It turns out no. Is it dietary fat? It turns out no. Is it vitamin deficiency? It turns out no. We spent a lot of money looking at vitamin deficiencies. Turns out it probably increases your risk of cancer, which is a little ironic. So just to get off the topic a little bit, we did these studies in the 2000s on folic acid. If you remember, at the time, there's a big wave of enthusiasm for homocysteine. Remember this?
Yeah.
So homocysteine was a risk factor for heart disease, and you could take folic acid and lower your homocysteine level. So there's big trials that looked at folic acid supplements. And it turns out that, and they said, well, it's going to reduce heart disease. It didn't. And then they said, well, it's going to reduce cancer. It didn't. But then when they actually looked at some of the studies together, and this was in the New England Journal of Medicine too, it actually increased your risk of cancer. And it's like, well, you know that the birth of chemotherapy was the anti-folates, right?
Right.
Because what happened when Sidney Farber did his initial studies is that he actually gave folic acid supplement, or folate, to cancer patients with the idea that it would lower their risk of cancer. It didn't. It accelerated their cancers, right? So then he switched and said, well, if it's bad, then I'll do the opposite. So I'll block folic acid, and that's the birth of chemotherapy. So it's like blocking folic acid is the sort of core of chemotherapy. Like, it's the origins of chemotherapy. So giving folic acid is not good, right? So that's why we saw this extra cancer. So it didn't turn out to be vitamin deficiencies. But what it did turn out to be is obesity and type 2 diabetes were actually big risk factors for these types of cancer. So breast cancer, colorectal cancer, also pancreatic, also liver. So, what is interesting again is this whole new understanding of nutrient sensors, what their role is in our body. So we actually have nutrient sensors, insulin, mTOR, and AMPK in our body that tells us when nutrients are available. And the reason they're important is because your body only wants to grow when nutrients are available. So if you reduce the availability of nutrients, and insulin, for example, is not just a nutrient sensor. We think of it as a metabolic hormone, but it's actually a very potent growth factor. We know that. Same with mTOR. mTOR is a nutrient sensor. When you eat protein, mTOR goes up. But mTOR is a very powerful growth factor, right? High mTOR, you're going to produce more growth. Low mTOR, you're actually going to go into autophagy and start to break down stuff. So your body only wants to grow when there's nutrients. So the nutrient sensor and the growth factor are actually exactly the same molecules. That's how integral it is to link growth and nutrient availability. So why that's important is for cancer is because if you have a lot of growth signaling, you're going to get more cancer because cancers love to grow.
Sure.
So that's sort of why it's important to treat these diseases of hyperinsulinism. So you reduce insulin, you're going to reduce your risk of cancer. So obesity, which is a disease of hyperinsulinemia, is going to increase your risk. Type 2 diabetes, which is a disease of hyperinsulinemia, is also going to increase your risk. And that's exactly what we found too, that these diseases actually cause way too much cancer. That's the sort of link between nutrition and cancer. It's not so narrow as, it's fiber, this and that. It's sort of this broad thing of insulin, mTOR, AMPK. And that's why something like metformin, which affects AMPK, might be very interesting as an anti-cancer agent because it acts along that pathway. Same thing with rapamycin, right? People are very interested in rapamycin because it acts along that mTOR pathway. And so it's super, super interesting because now you can actually say, okay, well, we know that mTOR is important. Can we modulate it in some way? AMPK is important. Can we modulate it in some way? We actually have drugs that do that already. So that's sort of an interesting area. Still tons of research to be done. But, again, this opens up a whole new possibilities that we never thought about to prevent cancer.
Sure. I think of the whole growth factor thing too. You look at children, if you don't feed children, they don't grow, and then they'll be short of stature, whatever. And then, I also, it's interesting. I think it was in your book that you talked about height and risk for breast cancer, right? People who are taller tend to have a little bit higher risk of cancer because they had more growth, right? I think that's sort of just in general, it's sort of the signals, whatever the signals are, whether they're innate within the genetic code or whether they're in your environment or both. Right, it probably has some effect on that, and but by simply knowing, I guess you can definitely see just by knowing by knowing the pathophysiology, sort of understanding what it is that causes the cancer, that now you can totally redirect your therapy into something where you may not have a cure for cancer in 5 or 10 years, but you're at least going to start probably heading down a more effective treatment path than where we were 20 years ago. That's how it always happens, right? It's like you slowly evolve as you get more understanding of the when you understand the root, you can attack at the root versus attacking the branches in the trunk, right?
Absolutely. And that's where you can say, well, what about changing the diet? What about cutting out sugar, for example, which is a huge risk factor for obesity and all this other stuff? What about intermittent fasting, where you're going to reduce all of your nutrient sensors? Because it's not like simply reducing insulin, you're reducing mTOR too, because you're reducing all kinds of stuff. And then, of course, when you go to the animal studies, of course, the only consistent thing that increases longevity is calorie restriction, right? And it's like, wow. This plays exactly into it because cancer is a disease of growth. So if the minute you start to restrict growth, you can do that by affecting nutrient availability and therefore perhaps reducing cancer. And it's like, well, this is a fascinating area. Now you can say, you can either try to mimic it with drugs, or you can simply apply it and say, okay, well, if that's the case, let us simply get a person who's overweight and use intermittent fasting, use low carbohydrate diets, and get them to a normal weight, because that should reduce their future risk of cancer or type 2 diabetes. If they have type 2 diabetes, you can reverse that with intermittent fasting, for example, or if they lose weight, like people lose weight, your type 2 diabetes almost always goes away or gets a lot better. Well, now you can actually not only get rid of that type 2 diabetes, but perhaps you can also reduce your future risk of cancer substantially. And that's huge, because this is like the biggest killer of Americans practically, right? And you can do something about it yourself if you have these other problems. And it's like, what a fascinating sort of story of medicine. It's like this, all the ways from the basic science to seeing how you change your understanding of cancer and how it affects what you can do to reduce your risk, to the treatments that we're developing now. It affects everything. The paradigms that we follow affect everything in terms of prevention and treatment, which is what, that's where the rubber hits the road. That's where it's important for the regular person. But you can only get there by understanding those paradigms in the first place. And that's why it's so important. And I tell you, most people don't even spend any time thinking about these sort of things. It just interests me. That's the reason I think about them a lot.
Yeah. Well, and it's interesting when you look at the causes of death and smoking is obviously a really high personal habit, I guess you'd say, that leads to death with cancer and COPD and heart disease and vascular disease. But you could definitely see if probably even obesity is not even, I don't think lots of cancer is even sort of attributed to obesity in lots of the statistics, right? But it'd be interesting if you kind of relook at that and say, well, some percentage of those are, related to obesity. And after reading your book, I started looking at patients I had who are coming for cancer surgery, and I'm like, wow. I mean, most of them are pretty overweight. Now, to be fair, most of my patients are overweight anyway. I mean, I am in the United States, right? And I'm in the Midwest. But I would say, like, someone with cervical cancer, they're almost, I mean, not everybody, but almost all of them, or uterine cancer, I should say, almost all of them are fairly overweight. Not like massively, but it's just an interesting thing. And there's obviously confirmation bias, right? So that's possible when I look at things. But
well, what's interesting is when you look at the population, so they do this thing called population attribution fraction, which is you take a risk factor, you multiply it by the population, and you say, okay, how much of cancer is related to smoking, say. And it's very high. And they did this analysis in 1981, and they repeated it in 2015, came to the same conclusion. So roughly 35% of cancers are related to smoking. So that's why we've been actually successful in reducing a lot of cancer, because there's less smoking now than 1980. So therefore, the number of people who smoke. But it's not that smoking is such a terrible thing. Like asbestos is much worse, but more people smoke than are exposed to asbestos, right? So therefore, when you multiply it by the population that's affected, smoking comes out as number one. Number two, which is right behind it at 30%, is diet. It's actually right up there with tobacco smoke as a cause of cancer. And that's stunning because we don't talk about that at all. And way above any of these other things that we do talk about, pesticides and chemicals and stuff, and they're important, but they're not affecting most of the population, as opposed to the diet, which affects every single person is eating, right? So it's like diet is actually a huge part of the population attribution fraction, PAF, of cancer. Is just not well recognized. And because we didn't know what part of the diet was important, we didn't sort of pay any attention to it, as opposed to smoking, where you could say, okay, stop smoking. So, it's been recognized in the literature exactly how important the diet is. It's just that there's so much sort of rancor and debate about what part of the diet is. It all gets sort of lost. And then people say it's about calories, and other people say it's not about calories and stuff. So it's all over the place, right? But the diet actually plays a huge role, and sometimes that gets a little bit overlooked because it's like it's compared to like all these other things which are 1 or 2%, like radiation, 1 or 2%,
radon,
radon and pesticides and stuff. Like it's 1 or 2%, not like 30% of your population attribution fraction, right behind us, tobacco, and probably soon to overtake it. So when you look at cancers, we're doing pretty well. So almost all cancers are going down over time, except for the obesity-related cancers. Those are all going up. Yeah. And that's crazy because every other cancer is going down. So it's like, hey, this is where the future of cancer medicine lies. Prevention of these exact diseases where we know what's going on. That is obesity, type 2 diabetes, hyperinsulinemia, our overnutrition. They're playing a role in causing more of these cancers. So liver cancer, for example, had dropped into the 1990s as we discovered Hep B and treated Hep C and treated it and all this sort of stuff. It's going back up. So it's about tripled since it's low. It's like because of fatty liver, right? And it's like, okay, that's crazy. That's a crazy statistic. Pancreatic cancer, same thing. It's going up. It's like, well, how are you going to get it down? Well, you can only get it down if you know the root cause of what you're actually treating.
Yeah. Well, and that was actually another thing, which I don't know if we have time to get into, but it's certainly the fact that the viral influences in cancers as well. I mean, they're well known, like human papillomavirus, hepatitis B, hepatitis C, well, I don't know about A, but that they definitely they are contributing to cancer, which again sends you that signal that is a unicellular versus a multicellular sort of conflict, and that there's an immune response that's very important in the development of cancer, or at least prevention.
It's this sort of chronic sublethal damage is the sort of key underlying, because that chronic sublethal damage, whether it's from viruses or from radiation or from tobacco smoke, exerts a selection pressure among those cells to become more of this sort of individual survivalist sort of cell. And that's, again, so fascinating to me, because I look back at medical school, and then I remember people saying, well, anything that causes chronic damage can cause cancer.
Yeah.
I'm thinking, that's interesting, because it's true. Like, you look at, gastroesophageal reflux or Barrett's esophagus.
Right.
That's stomach acid, ulcerative colitis. Well, that's just chronic inflammatory damage of the colon. Yet you almost always get cancer.
Yeah, right.
Why? Right? It's not because they're randomly mutating.
Right, yeah.
As you've exerted a selection pressure, which is acting in a Darwinian or evolutionary process, which, permeates all of biology, to regress into this primitive form. There's no extrinsic mutagen. There's no extrinsic, because it's stomach acid or it's autoimmune, right? It's like, that's crazy, because we knew that in the 90s. We just sort of ignored it when we went along this sort of somatic mutation. Oh, it's random mutations. It's like, but Crohn's colitis, ulcerative colitis, gastroesophageal reflux, that's just chronic damage. You get it, same thing, like hepatitis B, hepatitis C, which cause chronic liver damage, cause cancer. Hepatitis A and hepatitis E, which cause fulminant liver damage, but not chronic, do not cause it.
Right.
Because it's an acute insult and not a chronic insult, right? And so the same thing with radiation. Chronic radiation causes cancer, like radiation treatments. A single huge dose, like Hiroshima, causes very little cancer, which is, again, completely fascinating. And I didn't even know that. But the studies from the atomic bomb survivors showed very little excess cancer, like a tiny, tiny bit more, but not a lot, because it was a single acute event and not a chronic thing, because it has to be chronic and sublethal in order to act as a selection pressure. Right. And that's, it's like, oh, this makes so much sense now. It's such an interesting way to look at things.
Yeah, without a doubt. And I would encourage people to listen to our previous episode we did, which is episode 102. You can find that at theparadox.com/102. This one will be theparadox.com/107, which will also have show notes for and links to find Dr. Fung's book, Cancer Code, which I can't recommend more than I say. It's a great time for Christmas. It's great stocking stuffer. Although maybe reading about cancer is not that's something that people want to look to, but it is one that is going to, it will open your eyes to sort of a new understanding and a new way of just kind of looking at things, and maybe helping take care of yourself a little better. Also, links to all your other books will be there, and the website you've been on before. I guess that's pretty much it. I want to thank you so much for talking about your book, and I encourage everyone to read it, and hopefully you can stay safe up there in Toronto. Now, as they say from Game of Thrones, winter is coming.
Thanks so much. Thanks for having me on.
Thanks for listening to The Paradox. If you like what the doc is doing, please subscribe and leave a review on iTunes or Stitcher. And share the show with your friends. Become a supporting listener to get access to special bonuses at patreon.com/theparadox. Show notes can be found at theparadox.com.